All right, we're going to try this for about the fourth time. I keep getting interruptions, but here we go. This is our page 7. So page 7 is our page on quadratics. I don't know why my little document camera is not coming up, but let's see if I can make it show up. There it goes. Okay, so our document camera is up. So we're going to be factoring some quadratics. So you notice that I already started making some notes. This problem says that we are going to factor. It never says that we are going to solve. So please understand, factoring is a tool that is used to solve many problems, but we're only talking about the tool that is getting it into factored form. Second, when we talk about a quadratic, anything that has that x squared term in it, a is the coefficient of the x squared term, b is the coefficient of the x term, and c is the constant at the end. So when we do these problems, the first thing we do is we look for a greatest common factor. I'm going to put that out here. So what is the largest number that they have in common in terms of those coefficients? Well, of course, in our first question, since a is 1, there really is nothing in common through those. Let me see if I can get that to focus a little bit better. There it goes. And so what I want to do is pick two numbers whose product is 20, but whose sum, they multiply to 20 product, or sum or add to 9. And we're actually done right there. X plus 4, x plus 5. That's it. That was my job, was to factor that. Now for letter B here, we're going to come up with two numbers. And again, it has to be 1 and an 18, a 2 and a 9, or a 3 and a 6. But 3 and a 6 would multiply to negative 18 if 1 was negative. And of course, since the sum is negative, the larger of the two has to be that. So what we've got then is x minus 6 times the quantity x plus 3. And again, it says factor, so I'm stopping right there. Now, going on to this next problem, you'll notice the GCF may kick in. So like, is there any number that they have in common? And what I notice is that all of these values are divisible by 4. Here, if you look, all of these numbers are divisible by 5. Now, as such, we can play the same game that we did above. We're going to do a times c, 1 times negative 8, and 7. And I know that 1 times 8 would be 8, and 1 and 8 could make a 7 if this number was negative. And so this portion factors to x minus 1 and x plus 8. That's x minus 1 and x plus 8. And that 4 is still sitting in front. Similarly, this one needs a product of 30 and a sum of negative 13. But if the product is positive and the sum is negative, I need two negative numbers, namely 3 and 10, because 3 times 10 is 30. So we've got x minus 3 and x minus 10. So we're looking good. Now, moving a little bit further, these problems are going to get progressively harder. Now, when you look at these, you might go, oh, I hope that has a GCF of 6, but unfortunately 6 does not go into 33, nor does it go into 45. Here, 10 doesn't go into either one, but I can see that all of these values are in fact divisible by 3, so I can get a little bit better and make these numbers a little bit smaller. 3 times 2 is 6, 3 times 11 is 33, 3 times 15 is 45. Now, here's the first problem where we have to do the full story. 2 times 15 is 30, and 11 is our central term, and then 6 times 5 is 30, and 6 and 5 makes 11. So we're going to go ahead and make our little box thing, and we're going to put our 2x squared on the top, 15 on the bottom, 6x and 5x. And then I'm going to look for common factors. And I notice that both of these are divisible by a 2 and an x. And 2x times x is 2x squared. X times 5 is 5x. And 2x times 3 is 6x. And 3 times 5 is 15. That looks great. So my factors are x plus 3 times 2x plus 5. But again, don't forget that we had that 3 sitting out in front. And so this is my fully factored form. And by that same kind of idea, if we notice that everybody here is divisible by 2, that's going to get me a little bit closer. 5 times 9 is 45. 12 is right here. The only way that I can make that happen is a 3 and a 15. And of course, That would be a -3 and a +15 since their sum is positive. Again, back to the idea of making our box. I got 5x squared minus 9. And instead of writing 12x down here, I'm going to write a 15x and a -3x, which again together make that 12x. And then I just look for what they have in common. And these 5 and a 3 is nothing, but they have an x. So x times 5x, x times -3, and 5x times 3. And therefore my factors are x plus 3, 5x minus 3, and of course the 2 that was sitting in front from earlier, and I'd have my fully factored form. So we're looking like we've got it going on here. Should box those answers. Now, for 33 and 34, or 34 and 35, I think is what it really should be. This is really now getting into that idea of we're going to go a little further and say maybe try to graph these problems. So the axis of symmetry of a problem always starts at an x equals the opposite of b over 2a. So my b value is -12, and I'm going to do the opposite of that, and that'd be 12 over 2a, but 2 times 2 is 4, and 12 divided by 4 is 3. So it looks to me like my axis of symmetry is at 3, but my vertex happens if I plug in 3 for x and see what happens. So everywhere where I saw an x, I'm going to replace that with the number 3. Now, order of operations is very, very important because I'm supposed to square before I multiply. So 3 squared is 9, and 9 times 2 is 18. And a really nice thing happened here that we've really stressed this year, that if you have done this right, this number should be twice as big as that number, and it is. 36 is bigger than 18, and it's the opposite sign. So it looks like we're doing okay. And so my vertex is going to be the place where that comes together. So of course, my x value we figured out was 3, and my y value is going to be whatever I got, 18 minus 36 plus 11, and it looks like my answer has a vertex of 3, -7. And of course, my 1, 3, 5 pattern got multiplied by 2, so it's going to be a 2, 6, 10, 14. And I like to put dots because this pattern never ends. It goes on for all eternity. And last but not least, my y-intercept happens when you plug in 0 for x. And as it turns out, if you plug in 0 for x, this term goes away. 12 times 0 is also 0, so all you get is 11. It turns out that value, your y-intercept, is always just c. And so just to reiterate that one, if we did the opposite of b over 2a, that would be -6. Coincidentally, we got the number 3 again. So my vertex happens if I plug in the number 3. It's not always 3, but just these two problems happen to happen that way. And so I plugged in 3 into everything, and let's see what I got. I got -27 and 54. Notice the 2-to-1 ratio. -15, looking good at 12. So I plugged in 3. My vertex is at 12. And last part is my 1, 3, 5 pattern got multiplied by -3, so it's -3. From my vertex, I'm going to go down 3, and then down 9, down 15, down 21, etc. So remember, you find your vertex at 3, 12 right here, and I go over and down 3. And then I go over 1, and I go down 9. Then I go over 1, and I go down 15 if I'm going to graph that. And then my y-intercept, of course, is always c. So if I did this problem right, this graph is going to hit the y-axis way down here at -15. And that's a terrible looking picture. I probably should not have included it, but that's kind of how that process of that 1, 3, 5 pattern works. Hopefully that helped, and hopefully it actually worked this time. I'll see you back in class.